Right now, you should just see my title slide.
Yes.
Okay, great. So, I, as with a lot of the forum talks, I'm a rank beginner to all this. So if I get anything wrong or have trouble explaining things properly, if you know about it more than I do, please jump in. But this is an orientation to optics, uh, picking up a lot of concepts and equations and abbreviations that I've been hearing for years and finally get a chance to kind of look to in some depth. So I'm going to dive right in. What we're going to try to cover tonight is types of lenses and mirrors, a brief review of telescope types and binocular types, aperture, focal length and focal ratio, field of view and magnification, using Barlow lens and reducers, resolution, eyepieces, including eye relief and exit pupil, and image orientation. That seemed to be a good general introduction to the optics involved in astronomy. So types and lenses and mirrors. So simple lenses, which are just one piece of glass, come in several different flavors. Convert. I was used to calling these convex and concave, but I like a lot of references call them converging lenses and diverging lenses, as well as mirrors, and that makes a lot more sense to me. I'm used to remembering concave. It looks like a cave as you're entering into it, and all that. But converging lenses and diverging lenses just simply tells you what they do. So, converging lenses take parallel light rays and converge them to a focal point like this. And diverging lenses take the same parallel light rays and cause them to diverge from each other, where this is a real focal point. So with this lens, if you put a piece of paper here, you would see an image on it. With this lens, the focal point is more is virtual, not real. So if you put a piece of paper here, you really wouldn't see a picture. But that's the focal point of a diverging lens like this. So two types of simple lenses. There are also compound lenses that are simple lenses can only offer limited correction and magnification. Compound lenses can be used to add lenses together to correct aberrations, enhance image quality, and achieve higher magnifications with greater precision than simple lenses can. So this is a cartoony picture of them, but a lot of the best lens systems are compound like this. Types of mirrors in the same way, there are converging mirrors and diverging mirrors. So light comes into a converging mirror, reflects off the mirror, and converges to a true focal point. A diverging mirror causes the light to diverge from itself, or seemingly to originate from a virtual focal point behind the mirror. And telescopes use both types of mirrors as well as lenses. Types of telescopes. I want to do a couple definitions. First of all, optical tube assembly. I can't tell you how often I heard OTA hanging around the club before I finally figured out what it was. It's the part of the telescope that houses optical components such as the primary and secondary mirrors or lenses. And this is an example from Orion Optics of an optical tube assembly. The other term is optical train, which is an arrangement of optical components to guide a line of sight or a laser. This definition continues. I deleted the laser from Wikipedia. And this is an optical train down here from the James Webb Telescope. It's the optical train of the near infrared camera of the James Webb Telescope. So this is the path light takes through the James Webb until it gets to the imaging sensor. But that's how an optical train would be drawn. So those are terms that are going to come up periodically for the rest of the talk. Telescope types, simple refractors, meaning that there's only the original refractor lens here without any additional intervening lenses. Light enters from here, goes through a lens where it's refracted. This is a converging lens. and it converges to a focal point at the eyepiece, and the eyepiece takes it out to the eye. There's an example of a refractor from Celeston. Compound fractures, complex refractors do things differently, but the simplest refractor is this one lens and the eyepiece. Newtonian is a reflector telescope, meaning that it uses mirrors rather than lenses, at least in the main optical tube assembly. Light enters from the front, goes back to a primary mirror, which is, again, a converging mirror. It sends it to a secondary mirror, which reflects it up through the focuser and out through the eyepiece. So that's a Newtonian. You'll hear people, at least that my experience has been, people refer more to their Newtonian telescopes as Dobbs or Dobsonian telescopes. A Dobsonian telescope is a Newtonian telescope that has been fitted with a simple alt-azimuth mount. And that becomes what the mount plus the Newtonian telescope is the Dobson telescope. John Dobson originated this because it was a simple telescope, easily constructed or moved, that lent itself to sidewalk astronomy, which was his passion. Catadioptric telescopes combine both mirrors and lenses, which is what catadioptric means. So they combine refraction and reflection in an optical system. Lenses are referred to as dioptrics. Curved mirrors are referred to as catoptrics. So the combination together is a catadioptric. And catadioptrics, in addition to optical telescopes, include searchlights, microscopes, early lighthouse focusing systems, and telephoto lenses all use catadioptric arrangements of lenses and mirrors. So the two most common type of catadioptric telescopes are the Schmidt-Cassegrain. So light comes in here. It goes through a corrector plate, it's called, which corrects for light aberration and coma and things like that. Comes through the corrector plate, bounces off a primary mirror at the end of the telescope, back to a secondary mirror, and then through the focusing tube out into the eye. This is an example of one from Celestron, another diagram of the light path of one. And the Schmidt corrector plate is a complex shape that corrects spherical aberration caused by the primary mirror. So this corrects it before it even hits the primary mirror here. The other type of catadioptric telescope is the Maksutov-Cassegrain. I keep wanting to pronounce this Matsukov, even though I spelled it correctly here. So I may slip back to doing that until I stop thinking about it. The Maksutov telescope is exactly the same as a Schmidt-Cassegrain, except for the corrector plate. The corrector plate is called a meniscus reflector plate because it's bent like this. And it also apparently incorporates the secondary mirror to a greater degree. And these are therefore said to be more stable, require columnation less than Schmidt-Cassegrains because of the relationship between the secondary mirror and the corrector plate here. But otherwise, it's exactly the same as the Schmidt-Cassegrain telescope.
Craig, may I interrupt for a question?
Yes, please. Yeah.
One of the things that has confused me a little bit on some of the diagrams of the SCT as well as this, the secondary mirror appears to be not a diverging mirror, but the opposite. I can't understand why, if the light rays are supposed to be concentrated as they reflect through the system, why would you have a mirror that spreads the rays out rather than concentrating them towards the eyepiece?
I'm actually going to address this. I'm going to address this later on in the talk, but what it does, we're going to talk about that when I talk about focal length, because
Okay.
as it spreads the light out, it increases the effective focal length of the entire system. So if allowed it to come to a focal point here,
Yeah.
that would define the from here to here to here would be the focal length. But if it causes the focal length to be way out here, it extends the focal length. So it's why these are so efficient in achieving a long focal length without having a very, very long optical tube assembly.
Okay.
And I have diagrams that show this later in the talk, Don.
Yeah. Okay.
All
Good.
right.
Thank you.
Okay, great. Brief word about binoculars. What do the numbers mean? They're presented as magnification times aperture. So the 7 here would be a magnification of 7 times with these binoculars. And the aperture of the binoculars is 50 millimeters. These also state the field of view, but I'm going to mainly address these two. There are two general types of binoculars: Poral prism binoculars and roof prism binoculars. Poral prism binoculars, these work through prisms rather than through lenses, except up front and back here. But the light path is bent by prisms, and the arrangement of the prisms here is bulkier, not linear as they are in the roof prism binoculars, but it makes them easier to build. But they're more easily knocked out of alignment. If you drop these, binoculars are likely to be knocked out of alignment, whereas roof prism binoculars are not. They're cheaper, bulkier, and more easily damaged than roof prism, which are more expensive. The optical light path here is straight through with these prisms, but they're more expensive to make. So they're less vulnerable to being knocked out of alignment. They're generally lighter and less bulky than the pearl prisms, and as a consequence, they're more expensive. Aperture is the size or diameter of the primary lens or mirror in the telescope system. So this is looking down the tube of a refractor, and the aperture is simply the diameter of the initial main objective or main lens. This is looking slightly askew down a reflector. So this is a Newtonian telescope, and the light is going straight down here, and this is the mirror at the far end of this reflector telescope, and the diameter of that mirror is the aperture of that telescope. This is the secondary mirror right here, reflecting light up through and out into the eyepiece and a viewer's eye. So it's aperture is a measure of light gathering ability. We'll see its importance later on, and arguably it's the single most important consideration in choosing a telescope. So focal point and focal plane. This is a diagram of both a convex lens and a concave lens, or a converging lens and a diverging lens. The focal point is the point at which rays or waves meet after reflecting or being reflected or refracted, or the point from which diverging rays or waves appear to proceed. So here's a converging lens. Light rays come in parallel. We assume the light rays that enter our lenses in astronomy are parallel because objects are so far away that light is essentially traveling in parallel streams by the time it reaches us. So this focuses those to a point here. This point is referred to as the focal point, and the plane that is vertical. These stream of photons, because it passes through the exact center of the lens, is not refracted and passes straight through. That's referred to as the axis of that lens. So the focal plane is a plane that is perpendicular to the axis of the lens. This is the same arrangement, except that here light comes in and is diverged by the lens, and the focal point is where these rays come back here, and again as a virtual focal point rather than a real focal point. And the placement of the focal plane is again right through the focal point on the axis. Focal length is the distance from a lens or mirror to its focal point. And focal length can be referred to as a lowercase f or FL, uppercase FL. And this is the center of this mirror. And this is the focal point. So the distance from here to here is the focal length. Similarly, this lens, the focal length is the distance from the center of the lens to the focal plane or focal point at this virtual focal point back here. So for refractors and Newtonian reflectors, the focal point is relatively easy to see. So this is the main objective. So this is a refractor. This is the initial main refracting lens, which will take the incoming parallel light rays, bring them to a focal point, and the distance between the center of this mirror and that focal point is the focal length of that objective. The eyepieces also have their own focal points, but we're mainly talking about the objective or main lens right here. For a reflector, we're looking from, I guess, from the side. The light comes in parallel, reflects off of the objective mirror to a focal point here, and encounters this straight mirror that reflects it towards the eye here. The focal point here is if you extend these lines to where they would have been allowed to converge without the interposition of this mirror. That's the focal length. And those of you familiar with trigonometry know that this triangle here is the same as this triangle here. So this distance from here off the mirror to that true focal point, and from here to this focal point is the same because these are the same triangles. Catadioptrics are a little different, and this is where I think I'm going to talk about your question, Don. So again, same definition, but the light path is actually folded in a catadioptric telescope. The light rays come through the corrector plane. This is a Schmidt-Cassegrain here. They bounce off the primary mirror and bounce off the secondary mirror. And this secondary mirror is a diverging mirror. So these light rays, if this had just been a flat mirror or a converging mirror, the focal point would have been in here somewhere. But because this is a diverging mirror, these light rays don't bounce. They bounce off slightly wider than they would have and end up out here. And this extends the focal point. So the focal point in this system is from the primary mirror off the secondary mirror to this focus here. And it's the characteristics of the secondary mirror that extend the focal length. Is why the focal length can be many, many, many times the actual true length of the telescope because of the way this system works. And that's because it's got a diverging or convex mirror. Here is the secondary mirror. Don, does that help?
Yes, that's very good. Thank
Great.
you.
So focal lengths can be characterized as short, intermediate, or long. In general, focal lengths of 150 to 450 millimeters are considered short. Everybody's probably got their own definitions of these, but an intermediate focal length is 400 to 800 millimeters or 16 to 31 inches, and a long focal length is more than 750 millimeters or 30 inch. And we'll see the effects of changing focal lengths in a little bit. The focal ratio, or sometimes called F ratio, sometimes called F dash ratio, sometimes called F number. But I'm going to use focal ratio or F ratio for the duration of this talk, is calculated by the focal length of the telescope divided by the aperture of the telescope. So if you hold aperture constant, the longer the focal length, the higher the F ratio, which we're going to see in operation. So my two telescopes, I've got an 8-inch Newtonian with a focal length of 36 inches. So to calculate its F ratio, I divide 36 by 8 to get 4.5. I would express that as my telescope is an f4.5 telescope. My SCT, which is a 6-inch SCT with a focal length of 60 inches, the F ratio is 10. So that is an F10 telescope, a much longer F ratio than my Dobsonian. In general, F ratio indicates the amount of light that's collected and the speed at which photons are collected. So higher F ratio telescopes collect less light. They're dimmer at the far end where you can actually see. Lower F ratio telescopes collect more light. So people refer to telescope speeds. So telescopes that have F ratios of F5 or less are considered fast telescopes. F5 to F8 telescopes are considered medium telescopes, and telescopes greater than F8 are considered slow. Speed is of great significance to astrophotographers. So a fast telescope will allow an astrophotographer to expose a lot more quickly with a lot less time than a slow telescope. To observers, speed doesn't make that quite a critical a distance, but for the observer, the image is going to be dimmer with slow telescopes than fast telescopes. So the longer the focal length of the telescope, the higher the F ratio, and the dimmer the object is going to be in the viewpiece. Oh, I just included this as a reminder of what this equation was. So I will say that the other way to obtain a low F ratio, other than having a short focal length, is to have a big aperture. So if you've got a long focal length telescope, but it has a big enough aperture, it can still be a fast telescope, because both of these can be chosen when you buy your telescope to achieve a certain F ratio. The lower the F ratio, the more likely expensive your telescope will be, and the more complicated the lenses will have to be in order to correct for certain light aberrations that occur with fast telescopes. In addition, so I've already talked a little bit about this. So the telescope size, for a given aperture, the higher the ratio, the higher the F ratio, the longer the focal length and tube of the telescope, optical tube assembly. Conversely, the lower the F ratio, the telescope will have a shorter focal length and telescope tube for any given aperture. This doesn't hold true for if you vary aperture as well, but if you hold that constant, then F ratio is going to be directly proportional to the focal length of the telescope, and therefore the focal length of the telescope tube. It's why the catadioptric telescopes are so popular, is because you don't have such a huge telescope to achieve the F ratios that you want to, because of the folded light path and the ability to achieve a focal length without having the entire optical tube be that long. It also affects magnification range. We haven't discussed magnification yet, but we'll see in a couple slides that magnification is calculated by dividing the focal length of the telescope by the focal length of the eyepiece that you use. So a higher F ratio will allow higher magnification with the same eyepiece, because a higher F ratio will have a higher focal length most likely, whereas a lower F ratio, a fast telescope, will give you lower magnification with the same eyepiece, because of the way this equation works. Again, as a reminder, I can't see anybody if there are questions, so please interrupt me if there are, as Don did. Thank you, Don. Also, as I mentioned, lower f-ratio telescopes, faster telescopes, are more likely to have optical distortions or aberrations than higher f-ratio telescopes. So they need more complicated compound lenses and lens coatings to correct for those or avoid those, which is why they tend to be more expensive than the higher f-ratio telescopes. All right, so now we're going to go on to magnification and field of view. Magnification is defined as the size of an object observed through the eyepiece compared with its size when observed with the naked eye. So in the diagram here, this is the object, and this is the object at its focal point where it would be visible. And you'll see here that it can differ depending on the focal length. So the long focal length of this telescope allows its magnification, have better magnification than for the same object, a lower magnification. I'm going to show you that in a second. So magnification equals, again, the focal length of the telescope divided by the focal length of the eyepiece. So if you're using a telescope, you can't change for the most part, you can't change the focal length of the telescope, with exceptions to be discussed. But the easiest thing to do if you want to increase or decrease magnification is to change the focal length of the eyepiece. So each eyepiece is labeled with its focal length. And if you start looking for an object with an eyepiece with a focal length of 10 or 15, and you want to increase magnification, then you can drop the eyepiece to an eyepiece of maybe 5 or 6, which increases the magnification. There are some things to consider with that, but that's in general the approach. That the smaller the focal length of the eyepiece, the greater magnification. But we're going to talk about there are highest useful and least useful magnifications. So there are limits to how much magnification can be useful to you. So these are, I may have to stop sharing here because I want to go to these simulations here. Just a second. So I'm going to stop sharing. I'll come back to this. And I'm going to didn't start yet. Okay. Okay, so this is a simulation. These are very cool. What happened to it? Oh, here. Okay, now I'm going to share my screen again. Okay, now you should be seeing a screen called Geometric Optics. Yes?
No.
Nope.
How about now?
There you go.
Yep.
Yes.
Okay. So these are simulations. So this demonstrates the effect of changing. You can demonstrate a lot of stuff with this, but you can demonstrate the effect of changing the focal length, which is from here to here in this system, on the degree of magnification. So the index of refraction, changing that changes the focal length. So keep your eye on this, the little yellow circle with dot in the center, as I change it, that the position of that will change. And that's increasing. So I'm increasing now, I'm decreasing the focal length. Now this is the object, and this is the image, inverted as we'll see. Watch what happens to the size of the image as I extend the focal length. So as I make the focal length larger, the image gets larger. So choosing a longer focal length increases magnification, whereas choosing a shorter focal length decreases magnification. Got that? And if you take another lens, it'll do the same thing. If you change the focal length, it'll change the size of the virtual image. So increasing the focal length here will magnify that virtual image. All right, so that's all I wanted to do with that. So let me get back to my slideshow. Gonna stop sharing. I'm just finding the slide that I stopped at. Magnification. Now you should be back at the magnification slide.
Yes, you are.
Okay, great. Good. Those are fun simulations to play with. They're both from recordings of high schools that use these to demonstrate things to kids. It's really very cool. But I will move on from there, from my toys. All right, so we've already seen this to some degree, but the effect of the focal length of the telescope. One thing you can do at home, if we were in one spot, I would all in one place, I would demonstrate this to you. I've got a bunch of if you take the cardboard tube at the when you finish a roll of paper towels and the cardboard tube when you finish a roll of toilet paper, they're about the same size. So if you imagine those are optical tube assemblies where with the same aperture, they're the same diameter, but one has a long length and one has a relatively short length. If you look through and try this tomorrow or try this when you get a chance, if you look through the longer tube, the one with the longer focal length, and you compare that to the image you see in your yard or out in the street through the shorter tube, you'll see a much more restricted field of view, a much smaller piece of the object. And so that object, when it reaches your eye, is going to be greatly magnified compared with the object you see when you hold the shorter tube up to your eye. And it's a nice demonstration of how the differing focal length itself can cause apparent magnification of the field of view. The sacrifice you make by that, though, is that less total light reaches your retina. And there is a butter and toast analogy. So if you can imagine the size of the picture that reaches the focal plane of the telescope or your eye, your retina, magnification makes that whole thing bigger. So it's like if the size of your retina is a small piece of toast, magnification is achieved by making the size of the image that reaches your retina 3 times that size or 4 times that size. The problem is the same number of photons create that larger image that that created the smaller image before. So you're actually diluting out the photons. So if you imagine the toast being the size of the image when it reaches your retina or the plane of your retina, and the butter to be the amount of light of the photons, increasing magnification without changing aperture is achieved by increasing the size of the toast without changing the butter. So this spreads the butter thinner, meaning that there's less light or less photons in the piece of the image that you're actually seeing with your eye. And this is a demonstration of that. So this is a view of the moon through a telescope with a 3-inch aperture and a 70 times magnification. And you can see the image sharpness there. This is a magnified image through the same aperture telescope, but magnified from 70 times to 300 times. And you can see that there's much, much less light that reaches your eye, so the telescope is unable to resolve it. These dots get fuzzier, the image gets hazier. Now this third image is an image that's the same size, but same degree of magnification, but you've changed to a 7-inch aperture from the 3-inch aperture. And look at the difference in the image. A lot more photons reaching your retina with the 7-inch aperture. So even though you've got equal magnification, look what the telescope can do with more photons. These are much more pinpoint than these are. This is much more defined than this is. Resolution is much, much better. So it shows you that no matter how much you manipulate light with lenses and mirrors, there's really no substitute for photons, which is why aperture is so important. You can magnify, you can do everything to make the image larger, but without the photons, eventually there's a price to pay. And the price to pay is called highest and lowest useful magnification. So if you exceed the highest useful magnification of your telescope system, including the eyepiece, the image may appear blurry with less resolution, sort of like that middle image I just showed you was. And you can estimate the highest useful magnification that you can achieve by the aperture size in millimeters times 2, or the aperture size in inches times 50. So with my 6-inch SCT scope or my 8-inch Dob, the highest useful magnification I can achieve with that is 40. So when I'm out at Farish, I can choose a combination. I can choose an eyepiece that, when combined with the focal length of my telescope, will yield a much higher magnification than 400, but it won't do me much good because the image will start to get very, very blurry with less resolution. So the highest magnification I want to use with that telescope is 400. So that's with that aperture. The only way I can get higher magnification of the part of the sky that I want to see is to with visual observing, is to find an instrument with a larger aperture so I get more light in the system so I can magnify it highly. Lowest useful magnification, the problem is that with reflectors and SCTs or catadiopter telescopes, there's a central obstruction from the secondary mirror, and exceeding the limit of lowest useful magnification may cause this obstruction to become visible. So there's a lowest amount of magnification you want to use in addition to a highest amount. And this can be estimated by dividing the aperture in millimeters by 7 or by the aperture in inches by 3.6. Field of view goes hand in hand with magnification. Field of view is the amount of sky in degrees that you can see. There's true versus apparent field of view. The apparent field of view is the field of view that's written onto your eyepiece, or comes with the instructions for your eyepiece. That's the amount of sky in degrees that you can see through the eyepiece when it's held to the eye without being in the telescope. And that's the field of view reported by your eyepiece manufacturer. The true field of view is what you can see of the sky when you insert the eyepiece into the telescope. And it can be estimated from dividing the apparent field of view by magnification. So if we've kind of already alluded to earlier in the talk, the higher magnification you go to, the smaller your field of view. That's why often when people try to find things in the sky at night, they'll use a relatively high eyepiece focal length or focal length because it gives you less magnification and allows you to see a bigger part of the sky with which to find your object. Once you've centered on your object, then you can replace that eyepiece with a much smaller focal length eyepiece, which will increase magnification and decrease your field of view. So what you want to see occupies a much larger portion of the image that you see with your eye. Again, as magnification increases, true field of view decreases. All right, next I want to talk about Barlow lenses and reducers. Most people who buy sets of eyepieces will have at least one Barlow lens, if not a reducer, in the eyepiece. And a Barlow lens is a diverging lens that's inserted between the focal point of the main objective and the objective. So here's a refractor, we'll say there. So it's here's the main objective, and without this Barlow lens in there, the main objective focal point is here. You can see this is a straight line here. This is a straight line here. Inserting a diverging lens into this image train causes the focal length to be refracted outward, and the focal length is extended here. So what the Barlow lens is, it effectively increases the focal length of the telescope and therefore increases magnification and decreases field of view. So if I start with a 1200 millimeter focal length telescope and a 10 millimeter focal length eyepiece, my initial magnification before I insert a Barlow is, using this equation, is 1200 divided by 10, or 120. If I insert a Barlow, that essentially doubles the focal length of the telescope to 2400, then my magnification goes to 240. So a 2 times Barlow, it doubles your magnification. A 3 times Barlow triples your magnification. I've heard there are such things as 5 times Barlows, but the only ones I've ever seen used are 2 and 3 times Barlows. Reducers do the opposite. So reducer is a converging or convex lens inserted between the focal point of the main objective and the objective. So here's the original view, which is a straight line without. This is the original focal point. Putting in this converging lens causes the rays to converge much earlier in the focal train than they would have, effectively reducing the focal length of the telescope, which increases field of view and decreases magnification. Resolution is the ability of a telescope to distinguish between two closely spaced objects or details in an image. So resolving capacity, or something called referred to as minimum separable acuity, is how small the angular distance between two objects may be while they're still recognizable as two objects. And there are ways of calculating these for telescopes. One criteria is derived from refraction theory. Another criteria is derived from an empirical formula based on arc seconds. I'm not going to spend a lot of time on these because realistically, several of the references I read said that seeing conditions, air turbulence, thermal behavior of the telescope, usually limit resolving capacity to 1 arcsecond unless your conditions are absolutely ideal. So, these are helpful down to 1 arcsecond, but to choose an aperture that will get you to less than 1 arcsecond really requires extraordinarily good seeing conditions and dark skies. So what you would see if you have poor resolving power. So if you can, this is 2 stars in your eyepiece, say a double. If they're fully resolved, you would see this. You would actually see them as 2 distinct portions. If they're just barely resolved, you would see a fuzzy figure 8. And if they're completely unresolved, you'd see something that's really undifferentiated. You wouldn't even be able to tell. But if you look at something in the sky that looks like it's a fuzzy figure 8, then it may be a double that's just slightly beyond the resolution capacity of your telescope. Interestingly, Don's always talking about this at Strassenberg on Saturday nights, but Alcor and Mizar is the middle for most of us with human vision, is the middle of the 3 stars in the handle of the Big Dipper. And it's actually a double star, Alcor and Mizar. So this is seen through a telescope, and the brighter of the 2 stars is Mizar, the dimmer is Alcor. It actually turns out, interestingly, that Mizar is itself a double, Mizar A and Mizar B. And all three, Mizar A, Mizar B, and Alcor, are all doubles. So this is actually a 6-star system, which is felt to be gravitationally bound. And back to just being able to resolve Mizar and Alcor, the ancient Persians, Bedouins, Romans, and Japanese used the ability to distinguish between Mizar and Alcor as a test of vision or visual acuity. Nowadays, this is actually referred to by ophthalmologists as the Arab eye test, that if you can go out and you can distinctly see both Mizar and Alcor separately, you've passed this test. In ancient Rome, if you could distinguish between the 2 stars, you were eligible to be an archer in the Roman army. That was the test for eyesight good enough to be a long-distance archer. I really tried this afternoon to find this, but I don't know how you can have this be a test as opposed to the archer, the guy who just wanted to be an archer saying, yes, I can see those 2 stars. I don't know how they conducted the test to keep people honest, to be honest, but that is referred to as the Arab eye test. When I can, with my eyesight being as it is, I can never distinguish these two. But plenty of younger people that come to Farish say they can see this middle star as being a double with the naked eye, which is said to be true if you've got really good vision. All right, exit pupil and eye relief, which are both qualities of eyepieces. So exit pupil is the diameter of the beam or circle of light coming out of the eyepiece. So here's incoming light rays, here's the objective, here's the lens of the eyepiece, and here is the size of the cone of light exiting. And this can get larger or smaller. It determines where you have to place your eye. So you have to place your eye so that this cone of light is centered over your pupil to see everything. And you can calculate exit pupil by using the eyepiece and the focal length of the eyepiece and the F ratio of the telescope. So focal length of the eyepiece divided by F ratio of the telescope will give you the exit pupil size in millimeters. You can also use the aperture divided by magnification. So again, it's a better picture. So this is the light exiting from the eyepiece. This is the exit pupil, and this is pretty well matched here to the size of our pupil, our iris. This is looking at binoculars end on, and you can see the exit pupil here is smaller than the size of the eyepiece. Here's another picture of it where the exit pupil is much larger than the size of the eyepiece, than the size of our pupil. It's generally good to avoid mismatches between exit pupil and eye pupil sizes. So if the exit pupil is much larger than the eye pupil, it means that a lot of the image is bouncing off the part of your eye that doesn't emit light back to the retina. So you're losing a lot of light because the exit pupil is not appropriately sized. Also, if the exit pupil is much greater than the eye pupil, you'll begin to see this central obstruction in telescopes that have the secondary mirror, and it effectively reduces the instrument's aperture. If you have exit pupils that are much less than the eye pupils, it also delivers less light to the image because it's not taking you the very, very small exit pupil hits the retina, but not the entire retina. So you're only using part of your retina to see the image, meaning you're seeing a dimmer image. It does, however, provide higher contrast, better detail, and may reduce eye strain. So at times, this is a desirable situation. If you've got eye floaters too, you can see those with an exit pupil very much smaller than the eye pupil. Some references I found said that an exit pupil smaller than the eye pupil is ideal for observing deep sky objects, splitting double stars because of the better contrast, and actually planetary and lunar observation. Because of reduced overall brightness. So when you're looking at the moon, without a filter, without a aperture reducer, the moon is so bright that you can't see a lot of detail on it. So one thing that you can do is choose a system that with a small enough exit pupil that you can correct for that. It's, in my opinion, much easier to use filters and aperture reducers, but that's one way to see bright planetary or lunar objects. Eye relief is the distance between the lens of your eyepiece and the focused image. So this is exit pupil here. This distance is eye relief. And it's the distance your eye needs to be held behind the eyepiece to see images properly through it. It typically can vary from 2 to 10 millimeters. Larger eye relief, a bigger distance, generally allows a more comfortable viewing position, but it may be uncomfortable if it's hard to keep the eye in the right position. So it's hard to keep your eye matched to this distance. Your head's bobbing, it's windy, you're moving, you're shaking if you've got a mild tremor. So it's harder to do this. One thing that can help is eye cups. So this is an eyepiece, and they've got this piece of rubber that you can fold over, or some eyepieces have a thing that's on a screw, and you can screw it out and it'll extend out beyond the lens, because then you can actually rest your eye, the outer portions of your eye, on the edge of this eye cup, and it'll allow you to maintain a steadier distance to maintain the proper eye relief. The reason I like the screw ones better than this is that the screw ones actually allow variable distance in and out, whereas this is either all the way out or it's folded all the way back. There's no halfway, whereas with the screw ones it is. But of course, those eyepieces are much more expensive. With eye relief, general eye relief advice is that if the telescope is relatively slow, f8 or over, even short focal length eyepieces are usually okay, but for faster telescopes, eye relief can be an issue. And it may be so small so short that it's difficult to maintain proper position. It's a special issue for people wearing eyeglasses, because if you can imagine anybody not wearing eyeglasses can put their eye right at that position. If you're wearing eyeglasses, then you can put your eye right at that position, but your actual eye. So you can put your eyeglass against this, but still your eye may be back here somewhere. So because of the glasses, you can't get down to where eye relief provides the optimum picture. So some people like me tend to not try to observe without eyeglasses on. If you don't have astigmatism, that works. If you do have astigmatism, you need the eyeglasses to protect. So what you want to do is often you'll be in line to look at something on one of the telescopes, and the person in front of you has left this eye cup open. So what you want to do if you've got glasses and want to try using glasses is fold this down so you can get the glass right against the eyepiece to try to get your eye right at this eye relief distance. All right, lastly, I want to take on image orientation. So we all know that, or many of us know that you don't see this image upright in the eyepiece that you do when you look through the naked eye or binoculars or a spotting scope. The telescope system. So for a converging or convex lens, the image on the other side of the lens will appear inverted if the object is further away from the lens and the focal point. And for almost all of our observing, that's true. For the opposite, for a converging mirror, the reflected image will appear inverted if the object is further away from the mirror than the focal point. And I won't go back to this, but you can demonstrate this in these labs, in these simulations that I showed you earlier. One rule of thumb uses the number of optical elements. So, it's written that if your telescope has an even number of optical elements, not counting the eyepiece or corrector plate, the image is going to appear upside down. If your telescope has an odd number of optical elements, the image will appear right side up, but reversed left to right. I like this table a lot better. In fact, I now have this in my phone as a memory aid. So if the telescope is a simple refractor, an SCT without a star diagonal, or I should say catadioptric without a star diagonal, or Newtonian with the eyepiece sitting vertically right on top of the telescope, then the image will appear upside down and mirrored, reversed left to right. If you add a star diagonal to a simple refractor or to an SCT or catadioptric, then it'll make the image appear upright, but it'll still appear mirrored. So the question is, this is all very confusing, and it's very difficult to remember. And when you think about it, there's no up in space. What does upside down mean when you're looking at the moon or looking at a far deep sky object? Orientation doesn't really matter if one is simply appreciating the moon, a planet, or a deep sky object. If you're moving a telescope from one object to another, then it can help to have an understanding of your orientation. But what a lot of experienced star hoppers tell me is that it's easier just to move the telescope a little bit and observe what happens to the image to decide whether, if it's mirrored, then you got to move it to the right to cause the image to move to the left. If it's upside down, then you have to move the telescope up in order to cause the image to move down. Just to do a couple experimental pushes to figure out which way things are going to move, and then you don't really have to remember your orientation. It is helpful to remember orientation if you're star hopping using a star chart. So if the star chart is oriented right side up and left to right, then you can't move the telescope with your eye on the eyepiece because it's going to move a different direction than you would expect by seeing the image in the eyepiece. It sometimes can help to turn the star chart or atlas upside down. That at least accomplishes right to left reversal. Some star charts actually offer left, right, and upside down images. My iPhone Moon app, for instance, once I figure out what's happening in the telescope, I can tell the app, show me the moon right side up and left, right, reversed, if I'm going through a telescope where it appears that's the case. Or I can do one or the other. I can do just left, right, or I can do upside down, or vice versa, with it, to match this. And it's just a matter of uh, pressing a key on the app that will change the view. So even then, you may not need orientation awareness. And then finally, I guess when describing an object or calling attention to part of an object to another observer who's using a different type of telescope or configuration. So if you're trying to describe to somebody else on the phone who's looking at a supernova or a nova or um, a deep sky object, and you tell that person to look to the southwest to see a new bright light in that object. Well, in his eyepiece, that bright light might be to the northeast if it's reversed differently. So you need to be aware of your image orientation, as does the person on the other end, if you're trying to describe something who's not looking through the same eyepiece as you. Otherwise, people get more concerned with orientation than maybe they need to be. So we're nearing the end here. Summary. Uh, Concave mirrors and convex lenses cause converging effects on light rays. The opposite, convex mirrors and concave lenses, cause diverging effects on light rays. We've reviewed the different types of telescopes and binoculars. We've reviewed the primary effect of aperture uh, as a determinant of light gathering ability of your instrument. We defined focal ratio as the focal length of the telescope divided by aperture, indicates the amount of light collected. We've distinguished between fast and slow F ratios. Talked about magnification as calculated by I was going to say Finger Lake here, I'm getting tired. Focal length of the telescope divided by the focal length of the eyepiece. And if you want to increase magnification, choose a lower eyepiece up to the highest useful magnification limit. Barlow lenses and reducers increase the effective focal length or decrease the effective focal length, thereby increasing or decreasing magnification and doing the opposite to field of view. Talked about resolution, which is practically as good as you can get, about 1 arc second. And finally, we talked about exit pupil and eye relief and image orientation. And that brings me to an end. And I'm gonna one more slide. This is the first time I've ever given this talk, so please, if you have feedback about it, if I didn't get a concept correct or clear, then let me know about it, because the feedback I received in earlier such talks that I've given to the forum has been incredibly helpful in helping me refine the talk. If whatever get feedback I get tonight or tomorrow, I will go on Friday and revise this talk so I can make it better for the next time I ever use it. So please email me with any feedback you might have. And then I'm going to stop the share and invite any questions or discussion. Thank you very much for listening, you guys.
Thank you, Craig. Very good.
Yes, thanks, Craig.
Thank you.
The only thing I would add, Craig, or mention is that sometimes the choice of targets you want to look at determines what kind of instrument you want, whether it be a wide angle or long focal length, like planetary imaging, or deep sky, wide field view. You'd want a faster telescope.
Great, that's a good point.
You know what I mean? Like you couldn't. If you're looking for planetary detail, fast stop's not going to be the instrument for you.
Mm-hmm.
You know, that's that's all. Yeah.
Great. Yeah, thank you. I'll add that somehow.
Yeah, no, it's a really good talk though. Really enjoyable. Thank you.
Thank you. Other questions or thoughts?
It was an excellent overview.